Hello, good evening. Asmi is my name. I want to do a brief video on plastic deformations, and this will be one of the projects that I will be doing. And I just want to explain some key concepts whereby we are going to use the concept or the parameter that we're going to use during the simulation analysis. So basically, when we talk about plastic deformation, it's a deformation that causes permanent deformation as a result of applied load. So if you apply a load on a structure or on a beam, there is a limit whereby the beam can bear the load that you are trying to put on it. So if the load increases to a certain stage, and if you go beyond that stage, so the beam or the structure will become permanent deformation, and this we call total failure, and we don't want that. So if you go beyond the yield points of that structure, of that beam, of that material, so the material is going to fail. So we don't want that to happen. So in that case, I just want to do the simulation of I-beam simulation and see what is going to be the load that the high beam can bear. Definitely we have different type of I-beam. We have different parameter with respect to weight, the thickness, some other parameter like that. But this is going to be my module. Really, this is going to be my module that I'm going to use, and this is the true strain. This equation that I'm showing you here, these are the equation that I'm going to be verify. So I want to verify this equation. Maybe they are really good or they are something that is correct. Although we know it is correct because we've been using it for a long time. So I just want to use my research. I just want to do my research and verify with respect to this equation. So this is the stress equation, the true stress, and this is the true strain. So in engineering, we do not use true stress or true strain theoretically. So we use engineering stress and engineering strain. So there is little difference between those two. But practically, when we apply forces or force on any structures, we are getting true strain and true stress. So to make it easier, we convert it to engineering stress or strain. So this is going to be my modules. This is my high beam. My high beam is going to be fixed at this end, and there will be a load that is not constant on it. So the load increases at a certain rate or at a certain function. So you can see this is not a constant load. So the load is going to the load that I will apply on the high beam is going to increase at this rate, and the length of my high beam is going to be 400 millimeters. So after this condition, after my simulation and everything in ANSYS, I'm going to see a plastic deformation. You can see this graph. This is going to be the resemblance of the graph that I'm going to get during the ANSYS simulation. From here to here, it's elastic region, and from here to here is the plastic region. So this is the region that I'm very much concerned, because I don't want this region to occur. I don't want it to happen to any structure, because if this happens, this is going to be a total failure, and we don't want that. We don't want any device, we don't want any project or anything that we are doing to fail. So in that case, we need to take care. We need to know the maximum load that we could place on that structure or on that beams in such a way that is going to be safe for the environment, or is going to be safe for the product or for anything, so there won't be failure in that respect. In science, typically this is what happens when we got plastic deformation. Any material, we have atom inside the material, and there is a specific arrangement of different material depending on the material that you are using. Even in metal, we have different arrangement of atom in it. So that's why we have central cubic atom, phase cubic atom, hexagonal, and some other structural lattice arrangement that we have. This is what will happen in any of them if we have plastic deformation. When you apply force, this is the plane, this is the original place of this lattice arrangement. When you apply force more than what this plane can bear, the plane will shift to another area. If the force continue increases, so the plane will shift and it continues shifting from one place to another. So when this plane continue this way and it goes beyond this yield point, when this condition goes beyond this yield point, it will keep on shifting and deforming, and in that case it's going to turn to plastic deformation, and this region will be the region that we are going to have when the plane or when the material is undergoing plastic deformation. And if you return, by any chance, if you return the load from the material, it's not going to return to the normal shape again, so it's going to deform permanently. You will get a different shape. Even though you return the load, it's going to come down here. Instead of returning during the elastic region, is going to return to this point right here, but during the plastic region, even though you remove the load, it's going to return here, not here, and from here to here is going to be the plastic deformation, from here to here is going to be the elastic deformation. You know, if you can recall, I told you that when you apply load more than what the material can bear, there will be a plastic deformation and or permanent deformation, and that is the basic explanation of plastic deformation. So this is what occurs here, and this is what this graph is trying to explain, and this is the science behind this. So we should make sure that we do not apply more than what the beam can bear in order for us to have a shape or a safe condition. So this is going to be the I-beam. This is the shape. This you can see, this is the shape of high beam. You can see it's like high. I think they make the name from the shape. And this is the different sizes of high beam, different thickness. I'm sorry, this is very small. Let me zoom in so that you can see it. This is the width, this is the thickness of the width, this is the thickness of the flange, and these are the inches, and these are inches for different parameters that you could get from these different sizes of I-beam. So I got this data from this site, engineeringtoolbox.com/America wide flange steel beam, all those. I got this information from this site. So the true stress is as well the same thing as this equation, and the true strain as well the same thing as this equation. So this equation and the equation that I showed you earlier on, they are the same thing, but we just need to prove, we just need to do some proving before we can get this equation from this equation. So we just need to substitute some relationship parameter before we can get to that equation up there. So they are the same thing. So in the last section of this video, I would like to show you the ANSYS deformation that we are going to see. If I model that beam with the equations and the parameter, if I make my parameter to verify the plastic deformation, which means if I increase my load beyond the yield strength of the beam, whatever type of beam I chose, it might be steel, it might be stainless, it might be any beam, but I think I would like to use a structural steel or something like that. So if I choose my stress on this beam above the yield strength of this beam, there will be plastic deformation definitely, which means I'm going beyond this. I'm going beyond from this place to this place, so which means this beam is going to deform as you see it here. So in the next video I will show you the analysis in ANSYS and how I got to this place. I will show you everything in ANSYS. I just want to give you the brief explanation of my video and the project that I want to do to see how we can verify the plastic deformation. So we don't want this anyway. We don't want this to occur, and the only thing that we do in engineering is that we apply factor of safety. So factor of safety will limit the maximum load that should be applied on this beam. So the maximum load that should be applied on this beam is going to less than, or the maximum stress that we're going to apply on this beam is going to less than the yield strength of this beam. So that's the logic, is going to less than the yield point of this beam, and in that case the beam is not going to fail. Is going to be safe. It's not going to fail, and that's what we are going to be using to make sure that our design is safe and there is no failure at all. So I thank you very much for watching my brief video. I will upload it, and I will upload the second video through which we are going to go through the answers, and we are going to see how we can manipulate the how we can do the modeling, do the analysis on it, and see how we can get this result in answers. Thank you once again. I really appreciate it. Thank you very much. Have a nice